stationary points. So a stationary point is any point where the derivative is equal to 0. And we have three different types of stationary points. We have a maximum turning point, a minimum, and a point of inflection. At point A here, x equaling A, this is a position A, then what we have is a maximum turning point. And it'll follow this pattern: positive gradient, zero gradient, negative gradient. And we can use that bit of information in what we call a sign diagram to help us identify the type of stationary turning point that we have. At point B, we have a negative gradient, zero gradient, negative gradient. So that is a negative point of inflection. At C, negative gradient, zero gradient, positive gradient, and that pattern tells us that we have a minimum stationary turning point. And at D, positive gradient, zero gradient, positive gradient, so it's a positive point of inflection. This is what we saw at point A. At A, we had a zero gradient. To the left-hand side, it was positive. To the right-hand side, it was negative. So the shape here was up, flat, down. Therefore, we knew that we had a local maximum stationary turning point at A, f of A. So if we just threw in the value of x into the function, we'd get f of A. At point B, at x equaling B, we had a zero gradient. To the left-hand side, it was negative. To the right-hand side, it was negative. And the pattern was down, flat, down. Therefore, it was a negative point of inflection. At C, the pattern was down, flat, up. That told us that we had a maximum turning point. And at D, the pattern was up, flat, up. Therefore, a positive point of inflection. These here are known as sign diagrams, and we can use those to help us determine the type and also location of the stationary turning points in any function. All right, problem 1. Sketch the graph of y equals x squared plus 2x take away 8, showing all intercepts as well as the location and nature of the stationary turning points. So up until now, you were able to do your sketches and you were able to do all your intercepts, but you were not able to identify the exact positions of the stationary turning points. Now with calculus you can. So let's look at the stationary turning points. With the stationary turning points, the gradient dy dx will equal to 0. So here's our y function. Here's the gradient of it. I make the gradient equal to 0. And I now solve for x. And I see that where x is equal to -1, we have a stationary turning point. I now take the found x value and substitute it into the original y function. And that produces -9. So I now know that I have a stationary turning point at the position -1, -9. I do not know what its whether it's a maximum, minimum, or point of inflection. My next move is to create a sign diagram. So I have x equaling -1. I choose a value to the left-hand side, and I've just chosen one less than it, so -2. And I choose a value to the right-hand side of it, so 0. And if I substitute -1 into dy dx, I should always get a 0 for that. If not, I've done something wrong. And if I substitute -2 into dy dx, I get -2. Substitute 0, I get 2. So my shape here is down, flat, up. And if I look back to that previous page, that's in the shape of being a minimum. So I now know there's a local stationary minimum turning point at the position -1, -9. That's the calculus bit. Up until this point in time, you had no idea of identifying where, or by hand that is, what the nature and location of the turning points were. The rest of it is more routine. Y-intercept, simply substitute x equaling 0. I get 0, negative 8. X-intercept, make y equaling to 0 and solve for x. So I've got 0 equaling the quadratic. I factorise the quadratic. I apply the null factor law, and I get negative 4, 0 and 2, 0. Just a reminder that whenever you're giving your y-intercepts and your x-intercepts, to be 100% technically correct, put them as points. So now with all of that information, I've got my x-intercepts, I've got my y-intercept. I know it's an upright parabola because of the coefficient of the x squared. I also know the exact location of that minimum stationary turning point now as well. In the past, we just estimate that. Okay, so problem 2, we need to find the location of stationary turning points for this function here. Notice we're only after the location, not the nature. So I'll start with the f of x function. I work out its derivative. I make the derivative equal to 0. And now I solve for x. So I factorise the right-hand side, and of course I use the grid method, which is much more handy than the PSF method in cases where you don't have a 1 in front of the x squared. I now apply the null factor law to get x equaling 1/2 and x equaling negative 2. I will now substitute those found x values into the original function to get the corresponding y values. So firstly, substituting x equaling negative 2 into f of x will produce 14 on 3. So I now know that there is a turning point at negative 2, 14 on 3. I now substitute x equaling 1/2 into f of x, and that produces negative 13 on 24. And so I know that there is a turning point at x equaling 1/2, y equaling negative 13 on 4. Please notice that when you're listing your stationary turning points, you need to write it in this format as a point in brackets. Again, the question did not ask me to determine the nature, it just said the location. If I wanted to determine the nature, then I'd have to create some sign diagrams for each of these points, and I'd make use of the derivative to determine that shape. Alright, so I just want to go through the CAS approach. Remember, we're given this function f of x equals 2/3 of x cubed plus 3 on 2 x squared take 2x. What we had to do was work out the location of the stationary turning points. So my first job here is to define the function, so menu, actions, define, and then put in the function. Next step, I want to locate the x values. So what are the x values for where we have the stationary turning points? So to do this, I'm going to go menu, algebra, and solve. And I want to work out where the derivative is equal to 0. So menu, calculus, derivative. And I'm doing it with respect to x. And I'm looking for where f of x, which has been defined above, is equal to 0. And I am solving for x. And you can see I have those two positions, negative 2 and 1/2. They are the two x values. To work out their corresponding y values, I need to substitute those x values into the original f of x. So I want f of negative 2, and that produces the 14 on 3. And I also want f of 1/2. So you can go 1/2 if you like, or just 1 on 2. And that produces negative 13 on 24. So my two positions are negative 2, 14 on 3. And the second position is 1/2, negative 13 on 24, which is exactly the same as what we did by hand. Problem 3 is very similar to what we had in problem 2. We've been given a function, it's a cubic, and we need to use CAS. We need to find the location and nature of all the stationary turning points and also the intercepts, and then we sketch it. So to begin with, we define the function. So just to let you know, in blue here I've got some general ideas. Green are usually the CAS steps, and in red is what we would write down and show as part of our working. So we define the function, menu actions define, f of x equals blah, blah, blah. Find the x values of the turning points. So I just need to make the derivative equal to 0 and solve for x. So this is what I would write down. F prime of x equals 0, x equals -4 and 3, comma 2. So they are the two x values. How did I do it using my CAS? I bring up the solve function. So that's menu algebra solve. Then within that solve function, I bring in the derivative function. So menu calculus derivative, just like I did in problem 2. Put in f of x, put in that it's with respect to x here, make it equal to 0 and solve for x, and that will produce those two values. So they are the x values. I now need to work out the corresponding y values. So I will substitute x equaling -4/3 into f of x to produce 3, 9, 2 on 27. Do the same thing for 2 to produce -4. And that gives me these two turning points. Now I'm going to make use of sign diagrams. So I start with an x row, a derivative. I'm looking at the shape, and then I make a conclusion. So for where x equals -4/3, so that's roughly -1.33, a bit to the left, x equals -2, a bit to the right, x equals -1. If I substitute the -4/3 into the derivative, I'll get a 0, and that will be flat. The position to the left, -2, if I substitute that in, it'll be 8. 8 is positive, so therefore it's positive, meaning that it's increasing. And if I substitute x equaling -1, I'll get -3 for the derivative, and that will be decreasing. So it's up, flat, down. Therefore, I know I have a local maximum turning point at -4 on 3, 392 on 27. I'll do the same thing over here to determine the nature of the turning point at 2, -4. So I've got x equaling 2, a position to the left, I've gone with 0, a position to the right, x equaling 3. If I sub in 0 into the derivative, I'll get -8, and that'll be down to the right. If I substitute 3 into the derivative, I'll get 13. It'll be like so. And in green here, I've just shown you how you actually work out the derivative for various values of x. So you just want to go, remember f of x is already defined, so you just simply want to go menu calculus derivative, put in x here to show it's with respect to x. In here, put in f of x, which is already defined, and then given that symbol, x is equal to whatever you like, and in this case it's 3, and that will spit out a 13. So I've got my turning points, and I also know their nature. X and y intercepts. So x-intercept, y is equal to 0, so that will spit out x equaling that value, these values here. Y-intercept, simply substitute x equaling 0 into f of x, and that gives us an 8. And now I'm able to sketch it. Remember that overall, this function is a positive cubic. The value in front of the x cubed is a positive 1, so therefore I know it's going to be this basic shape. Up towards the right, something going on, and then continue on up towards the right. My x-intercepts are given. The exact value of the turning points are now known. The y-intercept is known, and I can do my sketch. You can see, in comparison to our technique in first semester, this is far more accurate because we know the exact location of the stationary turning points. Another little tip, make sure that when you're doing this that you are in exact mode on your CAS calculator. That way you will get the exact x-intercepts rather than decimal approximates. One of the more tougher questions because we've been given a function but it's got an unknown a and an unknown b, an unknown coefficient of x squared and an unknown coefficient of x. But we know that there is a stationary turning point at -2, 10, and and we have to work out what A is and what B is. So in this question, there's actually two bits of information. Firstly, if I were to substitute -2 into this rule here, the value of y would be 10. That will give us one piece of information, and from it, we'll have one equation. The second thing is that we know that at that position, -2, 10, it is in fact a stationary turning point. That means if we can work out to y dx from this original rule, then if we substitute -2 into that dy dx, the result should be equal to 0 because it's a stationary turning point at -2, 10. All right, let's deal with the first part. So y equals ax squared plus bx plus 7, and we know that -2, 10 is a point on this equation. So let's substitute x equaling -2, and we'll make y equaling 10. So there's the 10 there. Tidying things up, we get 3 equals 4a minus 2b. Let's use the second bit of information. The point 2, 10 is in fact a stationary turning point. So if we take our original y function and work out its derivative to ax plus b, then because it's a stationary turning point, we make dy dx equal to 0, and it's a stationary turning point at -2, 10, that is that the value of x is equal to -2. So I can substitute -2 into the right-hand side here. And now what I'll come up with is that b is equal to 4a. If I now consider this first rule, and instead of writing that first rule with a b, I write what it is equal to in terms of a, that is that b is equal to 4a, then I'll replace that b with a 4a, and I now have a line that involves just a. Tidying things up, I can establish that a itself is equal to -3/4. Just ignore this part here, guys, it's wrong. So I've found my a. I know that b is equal to 4 lots of a, so we can produce b pretty quickly. 4a equals b, substitute the found a value in, and I'll establish that b is equal to -3. So I've worked out a and I've worked out b. A is equal to -3/4 and b is equal to -3. Here we've got y equals ax squared plus bx plus 7. There's a point -2, 10 which is on this curve, and furthermore that's a stationary turning point. We need to use all of that information to work out the coefficient a and the coefficient b. How do we do this using the CAS? I'm going to start off by defining the function. So menu, actions, and then define. Instead of writing y, I'm going to write f of x equals the coefficient a being times by the variable x to the power of 2 plus the coefficient b being multiplied by the variable x plus the constant 7. It's really important, guys, that you make use of the multiplication symbol, because otherwise the CAS will see bx as just simply being the variable bx rather than b times x. All right, so it's defined. Now I've got two key bits of information. If I substitute x equaling -2 into this right-hand side, the value of y will equal 10. Also, if I look at the derivative of this function and I make that equal to 0, then the value of x needs to be -2. That's because it's a stationary turning point. So let's put this information into our solve function. So menu, algebra, and solve. And I'm now going to bring up the template. And I just want two functions. So the first bit of information there is that f of -2 needs to equal 10. So if I substitute -2 into f of x, the result will be 10. And then the second part is a little bit trickier. It involves the derivative function. So menu, calculus derivative, and I want it with respect to x, and we're talking about f of x. So the derivative of f of x will equal 0 given that x is equal to -2. So I just need to go and use the given that symbol. X is equal to -2. And I want to solve for A, and I want to solve for B. And there's my answer, just like I did by hand. So the tricky part here is this derivative part. Remember the way that the CAS works. So it takes f of x, works out its derivative. We need to make that equal to 0 for where x is equal to -2. So that's one bit of information. The other bit of information is that if we substitute x equaling -2 into f of x, the result will be 10. And with those two bits of information, it allows me to solve for the two unknowns, a and b. There's my A, there's my B.